Good morning, everyone, from sunny San Diego. And this is Turgay Gokar. I will be talking about two-dimensional erasure coded LTO tapes with Rail library configuration. Rail stands for Redundant Array of Independent Libraries. First section of my talk will focus on tape roadmap and tape format technology. Second section will focus on detailed tape errors and erasure code technology with Rail. Well, first of all, this is a often heard claim, is tape dead? I get asked this thing quite a bit of times. In my 20 plus year career, I was asked, is tape dead? Is tape dead? When is tape is gonna die? So many times that I basically lost count of it. However, recently, there's been some new activities around tape that is regenerated the interest in use of tape, especially at hyperscale. For instance, Jason Adrian from Azure Storage, Microsoft, back in September 17, 2020 at Fuji Data Conference, gave a presentation. The link is here. And what Jason said was, very interesting. He said, tape is not dead, but found a new home at hyperscale data centers. I couldn't say better. Then just recently, this last month, 2021, April 14, Andy Walls, CTO of IBM's Flash Systems division, did a presentation at Data Center magazine under the title of Tape, An Unexpected Renaissance. In his write-up, Andy talked about tape and data centers, and he said the following: nothing comes close to storing amount of data you can store on tape. We're talking pennies per gigabyte. Also, Fred Moore from Horizon at Fuji Summit also did his presentation, and he talked about tape being still alive for hyperscale data centers. So the common denominator here is tape is now with data centers. It's part of a tier storage. Now, why is that? Why all of a sudden this big interest in tape? Yes, we talk about ransomware and everything. However, the other part of the equation is the zettabyte data era. And with that comes TCO. So let's talk about tape's new home. Why is this? Like, for instance, Jason says specifically the roadmap. Tape roadmap is published by INSIC. INSIC is a nonprofit institution that we develop tape technologies. We write publications about tape, and we publish tape roadmaps. The website is available for everyone, and you can find various information there, especially with systems and applications and tape technology white papers. Part of that is there is a TCO paper, but then there is also this roadmap. When we look at the roadmap, we see the following picture here. The disk and tape, both magnetic storage. Disk has been enjoying a tremendous growth rate in areal densities back in late 90s, 108% per year. Then early 2000, it basically slowed down to 39% per year. And recently, it's at a level of 7.6% per year. But during that entire time, tape linear had enjoyed the same constant growth rate of 34% per year, which is incredible. We never increased it. We never slowed down. We kept maintaining that constant growth rate. And the same with projected estimated tape demos, which is also around 34% per year. So if you look at the blue diamonds, these are the tape demos. It's a line that it is parallel to the green dots, this 34% per year tape product line, which basically means a given tape technology in about 10 years finds its home at tape products. One perfect example of this is this data point here in 2006. There was a tape technology demo, areal density demo done by IBM, 6.9 gigabit per square inch. And about 10 years later, LTO 8, 2017, achieved 8.6 gigabit per square inch actual product in volumes, which is about 10 years later, we have a product at scale, durable, reliable, LTO 8 product with slightly higher than what was demonstrated by technology demo 10 years ago. So there is a proof of existence that technology demos do feed the actual products, especially with LTO. Now, when we start looking into this areal density demo, this areal density plot, we do need to go deeper because this is not the entire story. Why this big difference? Well, tape recently still enjoying 34% per year growth rate, where disk is around 7.6%. Why this is happening? The explanation of that is maybe best described by this plot. And this is a little bit of a crowded plot, but if you take your time, take a look at it, there is a lot to be learned from this particular information that is presented here. This is a three-dimensional areal density plot. We get areal density information. These are contour lines, red contour lines, as shown here. Starts at 15 gigabyte, goes all the way to 10 terabyte per square inch, which is you increase towards to the left corner. That's the track pitch and bit size being 1 nanometer. I just put that as a placeholder. X-axis is track pitch, Y-axis is bit size. So you can take a look at here, pick a data point, pick a product line like LTO 9, 18 terabyte. You basically say, what is this is areal density? It's 12 gigabit per square inch. And okay, what is the track pitch? Is about 1160 nanometers. What is this bit size? Bit length is just below 50, about 48 nanometers. So you know exactly where that is operating that produces that product. Then when you go to a similar capacity hard disk drive, you have to go way down towards bottom left corner. You find a 20 terabyte hard disk drive green data point here. Its track pitch is 40 nanometers. Its bit length is 12 nanometers, which translates into 1,240 gigabit per inch square, which is about 10 times the areal density of equivalent capacity LTO 9 tape. So this is the reason, this 100x difference is the reason why tape has huge opportunities in areal densities over the next 10 years compared to disk. For disk to achieve 100 terabytes and higher, it needs to go beyond 10 terabit per square inch areal densities, which is shown here. That zone is less than 10 nanometers track pitch, less than 10 nanometers bit length. In this area, you basically face not only supermagnetic limits, but also physical electromechanical limitations due to servoing, tracking, trimming, and so forth. Whereas tape can still achieve substantially higher capacities like this tape demo showed here at 310 gigabit per square inch, which equates to 580 terabyte capacities, still around 50 nanometer track pitches with close to 50 nanometer bit length. So basically, yes, tape has opportunities, but it also has its challenges, just like disk drives do. Tape's challenges can be summarized as dimensional stability and multi-track trimming with thin media moving at very high speeds in environmental conditions. Otherwise, you know, we have a fairly robust roadmap ahead of us. The dimensional stability and track trimming is some technologies that we can address and develop over the course of this time frame. So we feel confident that we can achieve this roadmap. Tape in its new home, you know, as we discussed the roadmap, it is clear that the reason why hyperscalers are very interested is because of the TCO and at scale. Otherwise, they still face the same challenges we legacy tape users face every time. Software, libraries, robots, media, drives, environmental conditions, temperatures, humidity, particulates, ability to manage drives at scale, you know, writing, reading efficiently. But you get in one key benefit besides TCO at scale, that is the durability. We, due to our very robust tape format, we are able to offer more than 11/9 durability for bit flips, bit rots, you know, that type of small random errors that, you know, pose a problem to the longevity of the data and the reliability of the written data. How do we do this? This is what we're going to go next. This is explained by this format chart. Now, this is, again, is a busy chart. I apologize for that. But what we're showing here is how your user data gets erasure coded, encoded, and written to tape, both ECC and physical perspective. Data is shown here is in the white box. That's your, any data you send, records, gets broken into 5 megabyte chunks. And these are data sets. It gets added with metadata and row encoded with C1 ECC, column encoded with C2 ECC. This particular data set is broken into 192 columns and 32 rows. Why 32 rows? Because there are 32 different physical channels. When you do this based on the linear density and the track pitch, which we discussed earlier, you end up writing this 5 megabyte erasure coded with metadata data set to a space on physical space on tape that covers approximately 2.8 millimeters height and 78 millimeters length. That's the area that this thing covers. And now this entire data is broken into 6,144 different chunks. Each chunk has a metadata, C1, C2, ECC capability, and then build into it. So you can lose these chunks any number of combinations and still be able to recover the data. How the data recoverability is dictated is by the C1, C2, ECC. C1 is a very strong long code word ECC, 249, 237 with 12 parities. C2 for LTO8 is 9684, 12 parities, but C2 ECC for LTO9 is going to be even stronger with same efficiency, 192 by 168, 24 parities. Overall efficiency is 83.28%. You add a little bit more efficiency, you lose a little bit more for the format, but typically this is the efficiency that robust tape format enjoys. So basically you can lose tracks, you can lose, be off track or have defects, you can still recover data with 11/9 durability. So now the calculation of 11/9 durability is explained in this chart. This chart is, you can probably see this thing in various publications, technology publications, but it's basically describes how tape format is used mathematically to calculate C2 or user bit error rate. User bit error rate that you hear is described in y-axis. That is calculated from the C2 input error rate. Like I said, in the previous chart, we have C1, C2. C1 detects errors, corrects them, provides that information to C2. C2 typically works in erasure mode, looks at the C1 output, says, these are my errors. I know how to correct them because I can correct up to 12 errors. So you look at the C2 input error rate, that's on the x-axis. From there, you say how many channels my drive is operating. If your drive is operating with full 32 channels, you come up with from x-axis to the blue line and go horizontally till it intersects the y-axis. That is your user bit error rate. Typical drives will operate at 10 to the minus 3 error rate. So if you go to this point here on blue line with all 32 channels operating, without any worn channels or worn head, that is the specific number for that. That's a typical drive. That means typical drive will provide you with LTO8 a better than 10 to the minus 19 bit user bit error rate. When that drive gets worn, is used at the head to tape interface increases in pole tip recession, then it will lose C2 input error rate. You'll have worse errors. But then you come down to here, which is about 2 to the 10 to the minus 3, which is about 10 to the minus 19 bit error rate. So we basically publish user bit error rates that you're familiar with, 10 to the 19, based on end of life type head configuration reading a good recording. This basically shows how robust the tape is because of this two-dimensional, orthogonal, highly interleaved C1, C2, ECC. And next session, we will be discussing about more real-world errors and why we need additional protection like copies and erasure codes and how we can develop these technologies. Thank you very much.